So we want to prove this result. So what we do is, it's fairly obvious that we need the residue theorem for this. So we're going to choose a contour on the S complex plane, and this is C. So what we want is this integral along here. So to use the residue theorem, we need a contour integral. We need an integral around gamma. So this is going to be part of gamma. So to complete the contour, we take this up to R, and one way, I mean, I'm going to show you this way. This is actually not the typical way people do it. People normally use a sort of circular contour, but actually I think this is slightly easier to prove. So we're going to have a contour of height R. So this point here is C plus IR. This point here is C minus IR. And then this point here, this is going to go to minus R. So this is minus R. Okay, don't really need to label all the points. Anyway, along here we've got Z equals X plus IR. Along here we've got Z equals X minus IR, and along here we've got Z equals minus R plus IY. Okay, so if we integrate this around the contour, so the integral we want is, well, we'll just call I, or actually, why not just call it as the thing we're trying to find in the end is f of t. So it's just equal to f of t. That's the integral we want, the inverse Laplace transform of f bar. So it's plus, and then we've got these three integrals. And obviously, by the residue theorem, this thing here is going to equal the sum of the residues. So all we need to do, should be equals, t equals this. All we need to do is show that these three integrals here tend to 0. So let's just write down what those integrals are. So its limits are r goes to infinity of the integral from here to here. So maybe it makes sense if I actually label these things. So A, B, C, D. Okay, so just for the time being, I'll just label them like this. So it's I want BC plus the integral limits r goes to infinity of CD plus the limit as r goes to infinity of dA. Okay, so I want to prove that each of these three integrals tends to 0 as r goes to infinity. So this first integral along BC, what is that actually? So okay, maybe I won't bother writing the limit yet. I don't have to write it each time. So along here we've got, sorry, this should have been S, not Z each time. So along here, we have the integral is from x equals c to minus r, and we've got f bar of s is equal to x. plus IR times e to the xt plus IRT. And then ds is just dx. So we're basically just interested in the magnitude of this. Does the magnitude of this go to 0? So I'm going to put absolute value here. Now obviously I can't work out what this is. But what I can do is say that it's going to be less than something. So what I do is say, well, I'm just looking at the magnitude of the terms. In the end, an integral is just a sum of things. So if there's anything of magnitude 1, like e to the IRT is absolute value 1, then I can just take it out, and because I know it's going to be less than or equal to 1, give it less than or equal to 1 contribution. So I now look at this term here and say, well, what's the worst that can happen? Well, the worst that can happen is that this integral here is going to be less than the integral of the maximum value of this thing. Okay, so basically this thing here, f bar, could do something like this, and I'm integrating over it. What would be the worst case? Well, the worst case would be if instead of this I just took the maximum value of it and then multiplied by the other things. Okay, so what I'm going to do is just take this out and just take the maximum value of this out. Okay, so the maximum value, this basically is going to simplify this integral, because then I can take the maximum value of this, just some constant, and if it's a constant, so it's a maximum value for x between minus r and c, I take the maximum value outside the integral, and that leaves me, I'm not interested in the IRT because that's just magnitude 1. Again, I'll put mod signs around this, and I just get left with an integral that I can do, which is simply the integral of e to the xt dx from c to minus r. Okay, again, I'm putting mod signs around everything. So ditto to this max thing, and I end up with, I just need to integrate this. So this is going to give me 1 over t times e to the minus rt minus e to the ct, okay, all mod signed. So as long as t is finite, r is positive, so this will all tend to 0, because we've said that f bar tends to 0 for any s as s goes to infinity, and obviously this this, I have to be careful, this is just some constant. So as long as this bit here is tending to 0, which it is, then anything tending to 0 multiplying some constant, as long as t remains finite, I'm okay. And then this obviously goes to 0. So in the end, all of this goes to 0 as r goes to infinity. Now that leaves us with the other integrals. But actually this one is very similar. The only difference is I've got a minus IR here instead of a plus IR. So basically, yeah, I just got a minus instead of plus here. So that works in very much the same way. I'm integrating this from minus r to c again for the x value. So that leaves us with the integral from c to d. So in this case, what do we have? Well, now we've got s equals minus r plus iy. So ds is now iy. So if we take the magnitude of that, y is varying from minus r to r. And we've got f bar of s e to the n s is equal to minus r t plus I y t dy. Okay. So I can take this thing outside the integral, and basically what I'm left with, because this is going to go to 0 as r goes to infinity, and y is also going, the y is going to infinity. So basically this, as r gets as r gets larger, this is going to infinity. So the argument of this is going to 0. So basically, I'm integrating something which is going to 0. Also, I'm multiplying by e to the minus rt. So obviously, as r goes to infinity, this is going to tend to 0 as r goes to infinity. So I've now shown that all three integrals are 0. Therefore, the integral I want is equal to the contour integral, and is equal to this integral here, and that, by the residue theorem, is equal to 2 pi I times the sum of the residues. So this integral f bar s t from a to b is just equal to 2 pi I times the sum of the residues. So moving this to 1 over this gives me the result I want to prove.